Alright kids, one last time. For those of you that need this quiz, good luck. Here's how you do it. For the homework, here we go. It says expand the binomial using Pascal's triangle to find the coefficients. Okay, seems easy enough. I know that when I expand a binomial to the power of 3, there'll be 4 terms, because the number of terms is always the power plus 1. I know those terms are going to be of the form x cubed y to the 0. No, you don't have to show y to the 0. I'm just showing it this time. The next term would be x squared y to the 1. The next term would be x y squared. And the last term would be technically x to the 0 y cubed. I know x starts at the power of the binomial, and the x goes down by 1. And the y starts at 0 and goes up by 1. So these are all the right terms. Now I just need the right coefficients. It says use Pascal's triangle. With a power of only 3, I can pretty easily build my triangle out. So we know that the first row is just 1. The next row starts and ends with a 1. Every row starts and ends with a 1. And any entries in the middle are the sum of the 2 entries above it. So this is a 2. Then the next row starts and ends with a 1. And I'll go 3, 3. Now the next row would be a 1 and a 1, a 4, a 6, and a 4. That's how you build the triangle out. But I know that the coefficients in the expansion of x plus y to the 3 are the entries of the row whose second entry is a 3. That's one way to think about it. Another way to think about it is it's the entries of the row that actually has 4 terms. We know that we need 4 coefficients. And I've got 1, 2, 3. Okay, this one is obviously the one that has 4. So my coefficients are 1, 3, 3, 1. So now just to simplify, clean this up. This whole first term is just x cubed. Then you're adding on plus 3x squared y. Then you're adding on 3xy squareds. And then you're adding on 1y cubed. So that is about as easy as this ever gets. There's our 4 terms of our expansion. For number 7, we're going to the power of 8. So this thing is going to have 9 terms, and we just have to do it out. They want us to use Pascal's triangle too, so no shortcuts to getting the coefficients. We know that we're going to get what? P to the 8th. Then that's going to drop down to p to the 7th, q. Then you're going to get p to the 6th, q squared. Then you're going to get p to the 5th, q cubed. Then you're going to get p to the 4th, q to the 4th. Oh God, I hate 4s on this writing tablet. That's a 4. Then you're going to get p cubed, q to the 5th, p squared, q to the 6th, p q to the 7th, and finally q to the 8th. So now how do I get the coefficients? Well, they wanted us to build out Pascal's triangle, so that's what we're doing. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, 1, 6, 15, 20, 25. Whoa. Dumb idiot. That's a 15. 6, 1. 7th, 1, 7, 21, 35, 35, 21, 7, 1. And finally, the row that we care about, the one that has 8 as its second entry. 1, 8, 28, 56, 70, 56, 28, 8, and 1. So now we know. We can pick up all those coefficients and plop them in to our expansion. So it's going to have a coefficient of 1, coefficient of 8, coefficient of 28. This guy will be the 56. Then this middle term is going to be 70. And then again, if somehow you still haven't noticed this, Pascal's triangle is symmetrical. So all these entries emanating out from the 70 are the same as the entries emanating that way. So after the 70 is going to come the same 56 again, then the 28 again, then the 8, and finally a 1. So I'm going to be a little bit lazy here. I'm not going to rewrite this any more neatly. I'm just going to say there it is. There's our expansion. So that's it. We're not using any fancy tricks for this. We don't have any coefficients on P and Q. So this is still supposed to be nice and easy. Even though there's 9 terms, this one was nice and easy. Next. Here, you're being asked to calculate NCR. And then this notation here is just an alternate notation that also just means NCR. So when you see parentheses and a number on top of another number, that's a shorthand notation representing the combinations function, not to be confused with the permutations function, which is something else. We want to actually evaluate this. So 9 over 2, or 9 choose 2. Every year there's someone who's shocked to find out that I'm saying 9 choose 2. There's always someone who thinks I'm saying 9 choose 2, like chomps on it with its teeth. No, 9 choose 2. It's sort of a shorthand verbal notation for 9 combinations of 2. You're literally choosing 2 things from a pile of 9 things. If I had 9 different candy bars and I said, hey, you can pick 2, then the total number of ways you could choose 2 out of the 9. You could say, give me the Snickers and give me the Twizzlers. Or you could say, give me the Snickers and the Three Musketeers. Or you could say, give me the Almond Joy and the whatever. But that's what this function is for. It's for calculating the total number of ways that you could do a certain event, like choosing 2 candy bars from a pile of 9 distinct candy bars. Okay, I'll shut up and I'll get to work. Just follow the formula. It says right here that we're going to do 9 factorial in the numerator. Perhaps somehow you still don't know what 9 factorial means. Well, 9 factorial, meaning the little exclamation mark, means 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2, all the way down to 1. So factorial is the product of all the integers from n down to 1. So these factorials tend to be very large numbers. The good news is, look in our denominator. We're going to do n minus r factorial. So 9 minus 2 gives me a factor of 7 factorial. We're also going to do a 2 factorial. So that's 7 factorial. That's a 7, 6, 5, 4, 3, 2, 1. So notice how all 7 of those factors are going to cancel with the last 7 factors of the 9 factorial. Now we still have a 2 factorial, so there'll still be another factor of 2 and a factor of 1 in the denominator. But man, we can really quickly cancel all of these guys. And then we can also cancel the 2 with the 8 to be left with a factor of 4. And we can see now that this whole shebang is just going to be whatever 9 times 4 is. So it's 36. So oftentimes these expressions are very easy to evaluate by hand. Let's pretend for a moment that you didn't trust your own arithmetic. Then you could bust out your calculator. With your fancy TI-84 pluses, you can just hit math and then go over to probability. Make sure you're in the probability heading and choose option 3, NCR. And what you should get now is the C with an empty space where the N and the R are. So you can type the 9 and type the 2. And you get your 36. If you've got an older calculator, then you'll have to type the 9 first. You must type 9 and then go get the NCR. Because when you choose NCR, instead of the little empty boxes, you'll just get 9 and then you'll get sort of the operation. You'll see NCR, the whole thing, between it. Then you'll type 2 and you'll on your home screen you'll see 9 NCR 2. And you'll still get 36. It just works a little differently. The interface is a little bit different. Every time they make a new calculator, they try to make little improvements to that interface. And this was a fairly new one, actually giving you places to plug in the N and the R. Alrighty, so that's that. Let's do the next one. It's 15 choose 11 this time. So this is going to be a little bit uglier, but not really. My numerator, there's going to be 15, 14, 13, 12. Go ahead and stop there, because what comes after 12? 11, 10, 9, 8, 7, 6. Well, that's just 11 factorial. Maybe leave that part as a factorial, because you know that down in the denominator, there's going to be another factor of 11 factorial. The other factor is going to be 15 minus 11, which is 4. So that'll be a 4 times a 3 times a 2 times a 1. So we can now quickly kill the 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. All of those factors cancel. Then I'm coming for, what, the 4 times 3, which makes a 12. Those cancel. Then the 2 can cancel with the 14, leaving a 7. So I can see that my final answer is going to be just a 15 times a 7 times a 13. And if push came to shove, I could do that by hand, right? Let's pretend that push has come to shove. 7 15s is what? 195? 105. It's 105 times 13. All right, I'm a big boy. I could do this out if I really had to. Three. Put down the 0. 1365. That's what I'm getting. Do I trust myself? Not really. I'll double check it on the calculator. But at least I'll check this one. 15, 7, 13. 1365. Good for me. All right, and I can really double check myself if I just go math. Probability, calc. What do we do? 15, choose 11. And 1365. So we know we're right. Be careful about overusing your calculator. You guys, there's going to be a question on the quiz where I straight up say you must evaluate this by hand. So I'm looking to see you expand these factorials, cancel those common factors, and evaluate by hand. So don't act like you can just press the buttons and get credit, because you can't. So 1365. So there's that. Moving on. Click. So this is supposed to be a no-brainer. 16 choose 16 is 1, because we had a general rule that said n choose n is always 1. Okay? Period. Someone in class brought up the fact that, n choose n technically would be n factorial divided by n minus n. That would be 0 factorial times n factorial. Well, luckily for me, 0 factorial, as strange as it is, think about it, it doesn't really make sense, because n factorial, like 5 factorial, is supposed to be the product of all the numbers from 5, 4, 3, 2, all the way down to 1. So 0 factorial doesn't make sense. You can't go from 0 down to 1. 0 is already less than 1. So somebody in their infinite wisdom decided that 0 factorial can exist, but we're gonna make it equal 1 so that it doesn't blow up our rule. We want our rule to still work. So if that whole thing is just 1, then you can see that n factorial over n factorial is 1. N choose n is 1. Okay, great. Awesome. Okay. Hey, by the same token, 16 choose 0 is also 1. Because it is. All right, so those are supposed to be easy to evaluate. Moving on. Here's where things get a little different. If I asked you to expand x plus y to the 14th, I mean, you could do it. It would take you forever, because isn't it going to be 15 terms? It's going to be x to the 14, and then x to the 13y, x to the 12y squared. You're going to be here forever listing out terms. So notice, we're not asking you to do the whole expansion. We're asking you to find this one particular term. So how do you do that? Well, what we should understand is every single term in our expansion is going to be made up of 3 parts. there's going to be the binomial coefficient, which comes from Pascal's triangle. It's going to be one of these numbers. And I don't think I've made this connection yet today, but all these numbers are generated by that NCR formula that we were just talking about. This is row 0, 1, 2, 3, 4. So in row 5, this first one is a 5, choose 0. This next 5 that comes from 1 and 4 getting added up, that's 5, choose 1. This 10 is 5, choose 2. This next 10 is 5, choose 3. And this 5 is 5, choose 4. And the one on the end is 5, choose 5. So all the entries of this row, the row whose second entry would have been a 5, is just all these little combinations where the n is 5. 5, choose 0, 1, 2, 3, 4, 5. Obviously we could hop down to the next row, and suddenly that row would be filled with 6, choose 0s, 6, choose 1s, 6, choose 2s. So knowing that relationship allows me to find, if I want the fifth entry in the row whose second entry is a 9 or whatever. That's technically, this is row 10 because the first row is row 0. But if you wanted that, technically it's called row 10, but it's 9, choose whatever. So that's the deal. All right, if that gives me my binomial coefficient, the value from Pascal's triangle, then the next bit is you take the first term, which in this problem is just x. That gets raised to some power. Then you take the next term, which in this case is just y. That gets raised to some power. So looking here, what do you know about p and q? You know that p and q would have to add up to 14. You know that. What else do you know? You actually know that if we're talking about the expansion of the 14, then this n would be 14 because that n is supposed to be that power. You would know that this r is actually the p or the q. And it turns out that mathematically, it doesn't matter whether you do the p or the q, because 14 choose, let's say, 3 is always going to be the same as 14 choose 11. If the two r values add up to 14, then they're going to have the same value. That comes straight from the symmetry in Pascal's triangle. We can see here that 4 choose 1 is the same as 4 choose 3. Way down deeper in the list, we would know that 14 choose 3 is the same as 14 choose 11. So I don't care if that's P or if it's Q. For my money, I'm usually starting at 0 and counting up, even though P starts at the 14 and counts down. So really, for me, this tends to be matching the Q, but it could go either way. Anyhow, I'm going to shut my mouth and just do this problem now. If you're after the term that has x to the 11th in it, then you know that you're after 14 choose 11 as a binomial coefficient. You want to be raising x to the power of 11. You want to be raising y to the power of whatever adds up with 11 to make 14, so 3. They didn't need to give you this 3. You could have found that yourself because you know it has to add up to 14. So often they won't. Often they'll say, find the coefficient of the term that has x to the 11th in it. And then you're supposed to know that the term, whatever term has x to the 11th in it, also has y cubed in it. And you'll have to make that connection yourself. Anyhow, I see my whole term now. My binomial coefficient is 14 choose 11. Now what on earth is that? It would be 14, 13, 12, and then 11, 10, 9, 8, 7, 6, 5, 4. Well, the denominator is going to be 14 minus 11, which is 3 factorial, so 3, 2, 1, and then an 11 factorial. So again, I can get these to cancel. The 3 and the 2 make a 6, which cancels nicely with a 12, leaving me with a 2. But I don't know what all this adds up to. 14 times 26? I don't want to do that. I can use my calculator to do that at this point. 14 times 26. 364. Now I've shown my work off to the side, so I know I'm going to get full credit. And at this point, if I'm a little bit sheepish, then yeah, go ahead. Use the built-in feature to make sure you're getting it right We said we wanted 14 choose 11. There you go. 364 was right. So that means my coefficient is 364. I get x to the 11 y cubed. That's it. There's your whole term. Next. Alright, this should be easy peasy. I still don't have coefficients on x and y, so I again know that all I want is my binomial coefficient. My power is 13, so it'll be 13 choose. It'll be either of these powers. I can literally do 13 choose 5 or 13 choose 8 because it comes out the same either way. Then if I want an x to the 8, I better take x and raise it to the power of 8. Super psych. Just kidding. X to the 5th. We want a y to the 8, so we'll take the y raised to the power of 8. That's it. This is the whole thing. 13 choose 5. How lazy do I want to be? I don't want to be that lazy. So it's going to be 13, 12, 11, 10, 9. 13 minus 5 is 8. So the 8 factorial is going to cancel in the denominator with an 8 factorial. There'll also be a 5 factorial. 5, 4, 3, 2, 1. So the 8 factorials cancel. 3 and 4 makes it 12. 5 and 2 makes it 10. So I guess I'm doing 99 times 13. Which of course is 13 less than 100 13s. Which of course would be 12, 8, 7. I'm calling it 1287. Now let's go see if I'm right. 99 13s. 1287. Is that what I said? Is that what I said? That's what I said. Alright, so it's 1287. X cubed y to the, or x to the 5th, y to the 8th. There's your, oh, super psych. It says only find the coefficient. So don't give me the x to the 5th, y to the 8th part. The actual answer is only the 1287. Did I screw that up in the last one? Yeah, this one also. It only says find the coefficient. So don't give me the whole term, just give me the 364. Anything else? No. Alright. So next, it says find the coefficient. Finally, we have a little more action here. When I go to expand this, I know I'm going to get a 12 choose. We want x to the 4th, so 12 choose 4. Now we'll get x to the 4th. But our other term is now a negative 2. And it would need to be raised to the power of 8 because we know it needs to add up to 12. So that means the 12 choose 4 is not the only coefficient I'll have. I'll also have a factor of negative 2 to the 8th. So that'll bump this number up. My final answer will not just be the number from the combinations formula or the number from Pascal's triangle. It'll be that number times the factor that's coming from the binomial raised to a power. So I think I'm ready to be lazy. Nah, let's do this out. What are we looking at? 12, 11, 10, 9, and then the 8 factorial cancels. Because 12 minus 4 is 8 factorial. There'll be a 4 factorial. 4, 3, 2, 1. Isn't this the same that we just did, actually? Kill the 8s. Let a 3 and a 4 kill a 12. Let a 2 kill a 5 and leave a 10. I mean, leave a... Kill a 10, leave a 5. So no, this isn't the same. This is 55 times 9. 55 times 9 being 55 less than 10 times 55, 550. So 495, obviously. Nailed it. I'm not even double checking that because I feel so good about it. So 495 is getting multiplied by x to the 4th, which is getting multiplied by 2 to the 8th, whatever that is. 2 to the 5th is 32, 64, 128. So 2 to the 8th must be 256 then. Now notice this is a negative to an even power. So this will come back as a positive 256. If this power was odd, you better bring that negative along for the ride. Okay? All right, I'm finally reaching for my calculator because I don't know what 495 times 256 is. $126,720. Now technically the whole term is 126,720 x to the fourth. But again, you are only asked for the coefficient. So on the quiz, give me the number only. Leave the x out of it. It'll be 126,720. Now one thing I can promise you is, put the comma in if you want to, or not. I've programmed it to accept it or not accept it. It doesn't matter. And I use the word program loosely. I didn't really program anything. All right, 15 goes to 16. This one should be very much the same. So we're going to do what? 11, choose 7. We're going to multiply that by x to the power of 7. We're going to multiply that by negative 3 to the power of, what could it be? Well, it's got to add up to 11, so I guess it's a 4. What's 11 choose 7? I don't care. You kids can do it by now, I presume. So I will cheat. We'll do 11 choose 7. 330. Then we've got an x to the 7th that doesn't contribute much. Then we've got a 3 to the 4th, which is 81, and it's going to be positive again. So 330 times 81, whatever that is. 26730. X to the 7th. That's the whole term. Again, I only want the coefficient. So 26,730 is the coefficient. And again, it's positive because we had a negative to an even power. If this was odd, then yes, this would have to be negative. When you give the coefficient, you include the negative if it's negative. All right, we're on to Roman numeral 4. We're now going to use the binomial theorem to expand. They do want you to expand the whole thing. So how's this different from the ones we did earlier? Well, we're not supposed to touch Pascal's triangle. We're not supposed to get the numbers from the triangle. We're supposed to get the numbers from our little 4 choose zeros, and our 4 choose ones, and our 4 choose twos, and our blah blah blahs. So to expand this, we know it's going to be, well, like I just said, 4 choose 0 multiplied by a 2x to the 4 multiplied by a y to the 0. Our next term will be 4 choose 1, 2x to the 3rd, and a y to the 1. Then we'll need a 4 choose 2, a 2x squared, and a y squared. We're on to a 4 choose 3, a 2x to the 1, and a y that's getting cubed. And finally, 4 choose 4, 2x to the 0, and a y to the 4th. Yeah, so I guess I'm pretty recklessly putting my exponents on the outside sometimes, on the inside sometimes, and sometimes that doesn't matter. I should probably say when it matters. It matters with the 2x. Here, if I had said 2x squared, all inside parentheses, then obviously that power of 2 would apply to the x only and not also the 2. So that's why I was pretty careful to make sure the 2 went on the outside for a term like this. Because now when I square this, I'll know to square the 2 to get the 4 and square the x to get an x squared. Here, it doesn't really matter that I put the 4 on the inside, because obviously y to the 4 on the inside and y to the 4 on the outside are the same. So it doesn't really matter. I was being a little sloppy there, though. Technically, your power should always be outside of the parentheses to ensure that it's affecting the entire term, the 2x, not just the x. All right, now what? Evaluate. We know that 4 to the 0 is 1. That's a 1. We know this is 16x to the 4th. And we know that anything to the 0 is another factor of 1. 4 to the 1, we know that. I don't know why I put an equal sign. 4 to the 1 we should know is 4. And then we get 8x cubed. And then we get a factor of y. Now 4 choose 2 I wouldn't know right off the top of my head. But I could evaluate it easily. 4, 3, 2, 1. It's going to be all over what? 2 factorial, 2 factorial, 2, 1, 2, 1. So you can pretty quickly watch as a 2 times 2 makes a 4, cancels a 4. 3 times 2 is 6. So this coefficient is 6. Then I get a 4x squared, and I get a y squared. Now 4 choose 3 is the same as 4 choose 1. So it's 4. And this is a 2x, and this is a y cubed. And 4 choose 4 is the same as 4 choose 0. That's 1. 2 to the x, or 2x to the 0 is 1. And y to the 4th is y to the 4th. So there's everything expanded out and simplified, but now we got to clean it up. Our first term will be 16x to the 4th. We'll add to that 32 x cubed y. We'll add to that 24 x squared y squared. We'll add to that 8 xy cubed. And lastly, we just have 1 y to the 4th. So there's your finalized expansion. And again, power of 4. I'm expecting 5 terms. 1, 2, 3, 4, 5. Done. Okay, next. Alright, so we're working in some radicals. Okay, sure, whatever. It should be the same deal. So what are we going to do? We're going to have 6 choose 0. We're going to have a root x to the 6th and a root y to the 0. We'll have a 6 choose 1 and a root x to the 5th, root y to the 1, 6 choose 2, root x to the 4th, root y to the 2. 6 choose 3. So there's 1, 2, 3, 4 terms. We need 3 more. 6 choose 4. 6 choose 5. And lastly, 6 choose 6. Root x to the 0, root y to the 6th. Alright, just because I don't feel like messing around with it, it's calculator trick time again. Let's see if it works. I don't know if it works on this. I assume it does. Go math, go prob, go NCR. We want all the 6s, right? So the trick is you can actually get them all. In your R's, use these braces. So go second blue brace and type in 0, 1, 2, 3, and you actually could stop there because we know that 4, 5, and 6 will be the same as 1, 2, and 3. But while we're at it, let's do them all. 4, 5, 6. I don't think you need to close the braces, but I'll close them anyway. I should now see, bladow, all my answers in braces. I can see the whole row of Pascal's triangle. It's going to be 1, 6, 15, 20, blah, 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 blah. So this is a good way to get multiples of these all at once if you want to. I wonder if you could probably just put it in here and make a table too if you wanted to. But this is a fast way. Using those braces you can get multiples. So 1, 6, 15, 20, just remember that. Alright. In fact, I'm just going to write it in now before I forget. This is a 1. Now we're supposed to already know that those are 1s. We're supposed to already know that these are 6s. but this being a 15 and 6 choose 4 being a 15 and 6 choose 3 being a 20. You wouldn't have those memorized, and there's no quick rule necessarily for just knowing those. So those are nice to get from the calculator. So what else is happening now? Well, root x to the 6. Remember, root x would be x to the 1/2, so that's going to be an x cubed. So you can see your first term is going to be x cubed. Next, you're going to have 6 as a coefficient. Let's talk this through. If you had root x, root x, root x, root x, root x, which is what root x to the 5th is, well, I just take them 2 at a time. Remember, these two are going to make normal x, and then you'll have a root x. So it's going to be x squared root x, and I think that's how I would put it. X squared with another factor of root x. And then you'll have a root y as well. So that's sort of the cleaned up version. I don't know how Ms. Butler's giving her answer. She may just be saying that this is x to the 5/2, 5 halves. Just use a rational exponent. I'm going to leave it like this, I think. Next, you're going to get 15. This will just be an x squared. And this will just be a y. So 15x squared y. That's a nice clean term. The next one is all the way up to 20. And it's going to be what? 1 normal x and 1 root x. So x root x. And y, or root y cubed, would be a y and a root y. Alright, next we get a 15, a normal x, and a y squared. We get a 6, a root x, and a y squared root y. And lastly, I always run out of room, but luckily I can just slide my work over and shrink it a little if I need to. You guys don't have that luxury, but I do. This will be 1, 1, and y cubed. So it's just going to be y cubed. Alright, there's my expansion. It can be cleaned up a smidge. This will be an x cubed. This will be 6x squared. If you've got 2 square roots, you can combine that. This would be root xy. Put them both under the same radical. Then the 15x squared y is fine. That's nice and clean. This is a little ugly though. I would write this as 20xy, the two guys that don't have radicals. And then the ones that have radicals can be combined into a single radical. So 20xy root xy would be how I express that term. Next, you've got a 15 xy squared, nothing to clean up there. Then you've got a 6. I would put the y squared first, and then have a root xy. And then finally you just have a y cubed. Now I see a root xy, but it also involves an x squared. I see a root xy, but it also involves a y squared. So those are not like terms, because this has an x squared, this has a y squared. So nothing needs to be combined any further, and nothing can be simplified further. So I would say that is the answer. I'm curious to see what Butler gave for her answer. Let's pause and find out. Okay, I'm back. So yeah, she did do it with rational exponents. She just got rid of the radicals, turned everything into those rational powers, and that's, it's fine. You can certainly do it that way. I think that's ugly. I think if a problem is given in radicals, you leave it in radicals, but that is just me. So I'd give my answer the way I gave it. She's given it the way she gave it, and it's fine. No big deal. We can both live together in harmony. Alright, moving on. Bonk. Hey look, it's the exact same thing. So let's do it. This one won't be bad. There's only going to be 5 terms this time, so that's good. We know that our binomial coefficients are going to be 4. Choose 0. Then it'll be the root x to the 4. Then it'll be the root 3 to the 0. That's our first term. Now this thing dings up by 1. This thing goes down by 1. This thing goes up by 1. But that's it. In fact, let me be the laziest man alive and do this. we basically just want clones of this, right? So I'm going to need another one. Come here, bro. I'm going to need another one. I'm going to need one more. Then I'm going to need another. Then I'm going to need another. Okay, train of thought. Lost it. But I'm back. 1, 2, 3, 4. Oh yeah, we need 5 of these, right? So you go in the garbage bin. You guys get smaller. You go over there. But this is going to be our expansion, right? We're going to need some plus signs. And then we just have to mess with our exponents and our binomial coefficient. 4 choose 0, then that'll go to 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4. My powers are going to go on the root x, it's going to go 4, 3, 2, 1, 0. And on the root 3, it's going to go 0, 1, 2, 3, 4. Maybe that's sort of helpful to see that literally they're all the same, and all that changes is those little number bits, right? In the binomial coefficient, we start at 0, and that ticks up by 1. And of course, you could start from 4 and go down, but I don't want to make things confusing. For the first term, you start at the 4, and that goes down, down, down. The second term starts at 0 and goes up, up, up. But this is it. That's literally my whole expansion. All I have to do now is evaluate it. And I think I know that 4 choose 0 is 1, because anything choose 0 is 1. And I know that 4 choose 4 is 1, because anything choose itself is 1. Then I know that 4 choose 1 is 4, because anything choose 1 is itself. And 4 choose 3 is 4. And so 4 choose 2 is the only thing I'd actually have to calculate. But, you know, from having seen Pascal's triangle a bunch as we studied, we probably should have it memorized that 4 choose 2 is 6. So there's all that. Now, what is root x to the 4th? That's just an x squared. And root 3 to the 0 is 1. So that's that whole term. Here's a 4. This is going to be, again, if anyone wasn't with me before, root x cubed is literally root x, root x, root x. And the two root x's make a normal x. So I would call it x root x. That's what I would call it. Another way to get there, of course, is this is x to the 1/2 to the 3. So that's x to the 3/2, which I guess is what Ms. Butler would give. That's not what I want to give. Looking at this, you can see it's x to the 2/2 times x to the 1/2. And there's your plain old normal x and your root x. It's x root x. You should call it x root x. All right, kill garbage. This is x root x, and this is root 3. This is a 6, a normal x, and a normal 3. This is a 4, a root x, and a normal 3, and a root 3. 3 root 3. This is a 1, a root, nope, not a root x. This is root x to the 0, so that's a 1. And this is a 9. So there's everything. Now just clean it up. We're looking at an x squared plus 4x times a root 3x, then a 18x, then a 12 root 3x, and then a 9. Can we combine anything here? Not really, because yes, we've got a 3x and a 3x in common, but this has a coefficient of 12 and this has a coefficient of 4x, so those are unlike terms. So this is the best we could do. Could we do any weird fancy junk? Kind of, but I wouldn't want you to. Just leave that alone. Give your answer like that. All right, cool. Next. Aha, some negative exponents. That's fine. Okay. So this will be 5 choose 0, x to the negative 2 to the 5, 3 to the 0. Okay, great. I choose to be lazy again. We know that the general form of each term is going to be 5 choose something, x to the negative 2 to the something power, and 3 to the something power. So I'm just going to make 6 of these bad boys, and then annotate them as needed. You. Get closer. You. Also get a little closer. Okay. Yoink. Yoink. Alright. 2, 3, 4, 5, 6. There you go. There's your expansion. Come here. Running out of room, so give it the old shrink-a-rooney. Alright, there's my whole expansion. So it's going to be plus, 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 plus. It's going to be 5 choose 0, 1, 2, 3, 4, 5. It's going to be x to the negative 2 to the 5, 4, 3, 2, 1, 0. It's going to be 3 to the 0, 1, 2, 3, 4, 5. All right, there's your whole expansion. Let's do this. 5 choose 0 is 1, because anything choose 0 is 1, and 5 choose 5 is 1. 5 choose 1 is 5, and 5 choose 4 is 5. That means I still need to figure out 5 choose 2 and 5 choose 3. Now again, from Pascal's triangle, I have it memorized that these are just going to be 10 and 10. But at the very worst, if you had to do this, then what is it? 5 factorial over 3 factorial, 2 factorial? That's 5, 4, 3, 2, 1 divided by 3, 2, 1 times a 2 and a 1. So you can kill the 3's, kill the 2, and you see the only factors left are 5 times 2. There's your 10. Once you figure out that one of them's 10, you know the other one is 10 as well. Oops. So this coefficient is 10. This coefficient is 10. Okay, now the rest is just evaluating. So this is x to the negative 10 times another factor of 1 plus. This is x to the negative 8 times a factor of 3. This is x to the negative 6 times a factor of 9. X to the negative 4 times a factor of 27. X to the negative 2 times a factor of 81. And x to the 0 times a factor of 81 times 3, which is 243. So there's everything. Clean it up. You were given a negative exponent, so I suppose you could leave it as a negative exponent, but it might be nice to clean it up a bit and say that this is 1 over x to the positive 10. This is 15 over x to the 8. This is 90 over x to the 6th. This is 270 over x to the 4th. This is 405 over x squared. And then lastly, just 243. Box it up. So I would give my answer like that. I would use positive exponents, meaning I have to pull all the x's into the denominator, and I'd give it like that. Again, out of curiosity, WWBD, what would Butler do? All right, bro. She and I are just like opposite people, apparently. So we agree. Yeah. All right. So she's leaving it with negative exponents, which is fine because typically, if you're given negative exponents, that's kind of a signal to go ahead and just use negative exponents. Of course, I would have said back here that when you're given radicals, that's a signal to go ahead and keep on using radicals, but she didn't. She used rational exponents. So she and I just differ. We just differ on what we like. I would rather see the positive exponents. She don't care. It's fine. Again, she does her thing, I do mine. Let's press on. Bonk. Hey, we're done. Now, false sense of security. If you understood this homework, that's cool and all, but you won't be prepared for the quiz. Remember the questions that were actually on the classwork. The things that had like 3x squared plus 5 over y, right? They were more complicated. We were raising this thing to the power of like 15 and telling you to find us the term that had x to the 20 in it or something, right? Find that term. Things were a little bit harder. I already posted a video on that classwork, so I just urge you to watch that. Go back and make sure you're looking at those problems that have more coefficients built in, that have variables in denominators, things like that. We said find the term that doesn't have a y in it. If we built a y into this expression and we built a y squared into the denominator over here, then there's some combination of powers that make the y cancel. We talked about that. That's on the quiz, so I would urge you to go back and watch the other video too. If all you did was this homework, it's not enough. Okay, great. That's all. I don't remember what I said. I think tomorrow night you have to do this by. So hopefully you're watching this thing tonight. It's 9:10. I should have this thing posted by 9:30. And that'll give you a chance to see me tomorrow. You period 6 and period 8 kids. You period 2 kids, if you can worm out of your period 2 class, then, or your period 6 or your period 8 class, feel free to barge in on mine. I don't care. As long as you, if you have no like assigned duties for period 6 or for period 8, come on into my class and ask questions. I'm sure the kids in there won't mind. I'm sure they'd be glad to have a voice asking questions. I know I will be. So you're all invited if you have your teacher's permission to cut the other class. All right, I gotta go. I hope you enjoyed this, the final video. All right, goodbye, pre-calc.